We are learning that the universe may be far stranger than our senses allow us to perceive. Each experiment hints at connections that extend beyond space and time as we know them. Some theorists suggest entanglement could be fundamental to spacetime itself. The structure of space and time might emerge from the web of quantum correlations. If true, this would imply that the universe is not made of separate objects in a void, but a continuous fabric held together by entanglement. The implications are staggering. It could explain why gravity behaves as it does, and offer clues toward a unified theory that reconciles quantum mechanics with general relativity. There is also a link to the holographic principle. Some scientists propose our three-dimensional reality is a projection of deeper two-dimensional information. Entanglement could be the thread that weaves together this projection. In other words, the seemingly separate events we observe are all manifestations of an underlying interconnected reality. Each particle, each photon is part of a cosmic conversation that stretches across the universe. The philosophical implications are equally profound. If particles can be instantaneously connected over vast distances, what does that say about consciousness and reality? Are we observers creating aspects of the universe by the act of observation? Does the universe itself possess a hidden network of connections that underlie everything we see? These are not mere thought experiments. They are questions that challenge the way we think about our place in the cosmos. Entanglement invites us to imagine a new vision of the universe, one where distance is an illusion and every particle is part of a vast interconnected dance. It encourages us to consider that the universe has a secret language, a way of communicating its underlying order that we are only beginning to understand. From the smallest particle to the largest structure in the cosmos, everything is entangled in a symphony of connection and correlation. As technology advances, we are starting to harness entanglement for real-world use. Quantum networks are being developed that could one day link computers securely across continents using entangled particles. Researchers are exploring how entanglement might be used to enhance sensors and measurement devices. Every new discovery opens the door to possibilities that were science fiction only a few decades ago. The universe is teaching us that connectivity is fundamental, not optional. The study of entanglement also reshapes our intuition. Classical physics tells us that objects exist independently and information cannot travel faster than light. Quantum entanglement defies both assumptions. Particles can act as if they are coordinated instantaneously, and their states are dependent on relationships rather than absolute positions. It is a new paradigm that challenges us to rethink what it means to exist and interact in a universe that is far more interconnected than we imagined. As we look ahead, the frontiers of entanglement research expand into ever more exciting territories. Quantum simulations might reveal new materials and medicines. Quantum communication could transform global networks. Philosophical and scientific inquiry into the nature of reality could reshape our understanding of time, space, and consciousness. The universe's secret language is becoming a tool for both practical innovation and profound insight. Next part can continue to explore the deeper implications of entanglement, philosophical questions, and emerging technologies. It will include examples of quantum teleportation, quantum networks, and the potential for entanglement-based understanding of consciousness and space-time. The narrative will remain engaging and broken into digestible paragraphs to maintain listener attention throughout a long video. Entanglement also challenges our notion of locality. Classical physics assumes that objects are only influenced by their immediate surroundings. Quantum entanglement shows that particles can influence each other instantly across vast distances. This is not a signal or a message being sent faster than light. It is a fundamental connection that exists independently of space. Understanding this changes the way we think about cause and effect and forces us to reconsider the very fabric of reality. Quantum teleportation is one of the most fascinating applications of entanglement. It does not transport matter itself. Instead, it transfers the state of one particle to another distant particle using entangled pairs. Scientists have successfully teleported information between particles across kilometers of fiber optic cable. This paves the way for quantum communication networks that are faster, more secure, and more reliable than anything classical technology can offer. Each experiment demonstrates the power and reality of entanglement in ways that were unimaginable just decades ago. In laboratories around the world, entangled particles are being used to improve precision measurements. Quantum sensors based on entanglement can detect gravitational waves, magnetic fields, and even minute changes in time with unprecedented accuracy. This opens new frontiers in astronomy, geology, and medicine. The ability to observe the universe with such precision relies on understanding and harnessing the subtle correlations of entangled particles. It shows that entanglement is not just theoretical, it is practical and transformative. The implications of entanglement for understanding consciousness are deeply intriguing. If reality is fundamentally interconnected at the quantum level, then observation itself may play a key role in shaping outcomes. Some theorists speculate that consciousness interacts with entangled systems in ways we are only beginning to comprehend. While these ideas are speculative, they push the boundaries of both science and philosophy. Entanglement suggests that the universe is participatory and that our observations are more than passive recordings of an external world. The relationship between entanglement and the multiverse is another area of speculation. Some interpretations of quantum mechanics suggest that every quantum decision branches into multiple universes. Entanglement could be the mechanism that connects these branches. If true, then each entangled pair might be part of a vast cosmic web linking parallel realities. Exploring these ideas is not just science fiction. Experiments in quantum computing and particle physics provide data that could one day validate or refute these radical concepts. Quantum networks are emerging as one of the most exciting areas of applied entanglement. Scientists are designing systems where multiple nodes are connected by entangled particles. This would allow instant correlation of information across global distances. Such networks could transform the way we communicate, compute, and interact with data. Governments and private companies are investing heavily in this technology. The future could see a global quantum internet underpinned by the same principles that govern the behavior of entangled particles. The challenge of visualizing entanglement is profound. Unlike classical objects, particles do not have definite positions until measured. They exist in a superposition of states. Entangled particles share these superpositions. When one is observed, the other instantly reflects the correlated outcome. This is deeply counterintuitive. Yet, repeated experiments confirm that nature operates this way. Accepting this requires a shift in perception. We must learn to think in terms of relationships and correlations rather than isolated properties. Entanglement also has implications for energy and information. Some researchers are investigating whether the correlations between particles could be harnessed to transmit energy or information in novel ways, while faster-than-light communication remains impossible. The underlying principle of instantaneous correlation offers new avenues for understanding the limits and potentials of information transfer. This is an area of active research that could redefine our technological landscape. As we delve deeper into quantum entanglement, we begin to see its presence in nature. Entanglement is not limited to laboratory experiments. There is evidence that photosynthesis in plants relies on quantum coherence and entanglement to optimize energy transfer. Some studies suggest that birds navigate using entangled particles in their eyes. These discoveries hint that entanglement is woven into the processes of life itself. The universe is more interconnected than we ever imagined. Philosophically, entanglement raises profound questions. If particles are fundamentally interconnected, then individuality at the quantum level is an illusion. Everything is linked through invisible threads of correlation. This perspective challenges our understanding of identity, causality, and free will. It invites us to consider that separateness is an emergent phenomenon. At the deepest levels of reality, everything participates in a cosmic dance of entanglement and interconnection. The measurement problem continues to be a central mystery. Observing one particle affects its partner instantly, but the mechanism remains elusive. Does the universe choose outcomes at random, or are there hidden variables we have yet to discover? The search for answers drives both experimental and theoretical physics. Bell's theorem and subsequent tests have ruled out local hidden variables, but the question of how entanglement works in detail remains open. Each experiment pushes the frontier of our understanding. Entanglement is central to the development of quantum computing. In classical computers, bits exist as 0 or 1. In quantum computers, qubits exist in superpositions and can be entangled. This allows quantum computers to process massive amounts of information simultaneously. Entanglement is the engine that enables quantum algorithms to outperform classical ones in specific tasks. Solving complex optimization problems, simulating molecules, and advancing artificial intelligence all rely on harnessing the subtle correlations of entangled particles. The future of quantum cryptography relies on entanglement. Traditional encryption methods can be broken given enough time and computational power. Entanglement-based cryptography uses correlations that are guaranteed by the laws of physics. Any attempt to intercept the entangled key changes the state of the particles and reveals the intrusion. This principle offers a level of security unimaginable with classical methods. As our world becomes increasingly digital and interconnected, the importance of quantum security will only grow. Entanglement also inspires new ways of thinking about time. Classical physics treats time as a sequence of independent events. Quantum entanglement suggests that correlations can exist across time in ways that are not yet fully understood. Some researchers are exploring temporal entanglement, where events separated by time are linked. This could have implications for understanding the arrow of time and the emergence of causality. Entanglement is not just spatial, it may also be temporal. Our understanding of reality is fundamentally altered by entanglement. What appears random or independent at the macroscopic scale may be deeply correlated at the quantum level. This challenges the way we interpret causality and locality. It suggests that the universe is a coherent whole rather than a collection of isolated pieces. Entanglement provides a window into the interconnected structure of the cosmos. It is a reminder that there is more to reality than what we see with our senses.